I want to take a moment to say thank you to my newest Patreon member, William Halprin. I can't emphasize enough how helpful it is to have supporters on Patreon and how encouraging it is to me to keep making these videos. I also want to take an opportunity to thank again my other Patreon supporters, Sanjayan, Antonio, Patrick, Michael, and Afshan. Thank you very much. If you haven't already, please consider joining, and whatever you do, please subscribe. It lets YouTube know you like these videos, and please keep commenting. Okay, we have finite sets conquered. It's time to start looking at infinite sets. This video is going to be relatively short. I'm going to suggest a different way of thinking about what it means for a set to be infinite. So what do we mean when we say an infinite set? I think we all have some kind of a sense that it means, huge, or it goes on forever, or never stops, or you'll never reach the end. You can add one and still have infinity, and so on. Right? Infinity is that number that's out there past all the other numbers. And that leads to all those mind-bending paradoxes that YouTubers are so fond of. The Banach-Tarski paradox, Hilbert's hotel with an infinite number of rooms, and so on. So we just spent 5 weeks looking at finite sets. First, defining a finite set as one that has a bijective correspondence with a section of positive integers, and that the size of that subset of the positive integers is the, quote, cardinality of the finite set. Then we proved that the cardinality of every finite set is uniquely determined by that set. So that is, if you have a boxcar full of marbles, there's a specific number of marbles in that boxcar, even though it would be impossible for us ever empirically to prove what that number is. So that was the whole point. We all have an intuition that there's a specific number of marbles in the boxcar, but we're never going to be able to prove it by taking them out one at a time and counting them, because it would take years to do that. Inevitably, there's going to be a mistake. We'll never know that we got it right, and so on. That was what we had to spend several weeks proving, that yes, there are, in fact, a specific number of marbles in the boxcar. So what is an infinite set, then? All we mean when we say a set is infinite is that the set does not have a cardinality that is uniquely determined by the set. That is, there is no bijective correspondence between the elements of the set and a section of positive integers. That's all that infinite means. That statement is so simple and so non-committal, and yet from there we end up with a hotel with an infinite number of rooms and can magically make two spheres out of one. So definition. A set A is said to be infinite if it is not finite. It is said to be countably infinite if there is a bijective correspondence F from A to the positive integers. So notice, that's almost exactly like the definition of finite. The only difference is it's not a finite set of positive integers. It has a bijection with all of the positive integers. And the fact that countably infinite means that there is such a bijective correspondence implies that we might be making another step, right? Because are there sets that do not have a bijective correspondence with the positive integers? That's the pending question, right? Okay, so example. I claim that the set of all integers is countably infinite, meaning that there's a bijective correspondence between the set of all integers and the set of positive integers. And it's easy to make a function that will demonstrate that. So when n is a positive integer, we just multiply it by 2. So we basically spread it out, right? So we have 1, 2, 3, just spread it out to 2, 4, 6. And then if it's 0 or negative, then we multiply it by -2 and add 1. So 0 would be 0 plus 1. So this would go to, so 0 would go to 1. And then -1, that would make 2 plus 1 would be 3. So -1 would go to 3, and so on. So we just fill in the minuses with the plus. Okay? So how bizarre is this? Instantly, we end up with bizarre results. We just proved that there are not more integers than there are positive integers. That's insane. Or to put it another way, one might say that there is no set number of elements in this set. A boxcar has a finite number of marbles. It has only one number of marbles, only one cardinality, even though that number is gigantic and physically unverifiable. An infinite set does not have one number of marbles or one cardinality. In fact, it can have 2 or more different numbers of elements. I mean, obviously, there are twice as many integers as there are positive integers, right? That's obvious. And yet, because there exists no bijection between the set and a section of positive integers, there is no definitive number of elements in either set. I know this is a strange way of thinking about it, but consider that according to the definition, infinite does not mean it goes on forever. It doesn't mean infinitely many. Rather, it means indeterminate. You cannot determine the number of elements in the set. That's all it means. We don't know how many elements it has. Therefore, it's impossible to determine that all integers is a bigger set than positive integers because we don't know how many are in either one. So how can we say they're different? If you think about it that way, does that make all of the, quote, paradoxes surrounding infinite numbers a little less mysterious? If we can't determine how many elements are in the set, why would we object to showing that there are, in fact, different possible numbers of elements? Maybe that's not so mysterious after all. So, another example. The product z plus cross z plus is also countably infinite. So this is the positive integers crossed with the positive integers. What is that? It's the integers in the first quadrant, right? So if we look at that, we can see possibly a way to count these that will show that there's a countably infinite number of them. If we start with A1, and then we call this A2, A3, so we go this way, and then we go back down here, A4, A5, A6, so we go up here, then we go back down again, up here, etc. Then we can redraw this or sort of rearrange it a little bit so that we have one here and then a stack of 2 and then a stack of 3 and so on. So a picture isn't a proof, of course, but it kind of suggests a way to do this. So first we're going to define a bijection from the cross product to a set A. And A is going to be this set. So A it's not all of the integers, of the positive integers crossed, it's just this subset of them. So first we're going to define a bijection from the cross product of the positive integers into A, where A is a subset of the first quadrant, which consists of the points x, y, where y is less than x. So everything where x is bigger than y is in this set, okay? And we'll define this bijection as f of xy equals x plus y minus 1, comma y. So let's check that this is right. So we're going from this set into this set. So 1, 1 is 1 plus 1, 2 minus 1 is 1, comma 1. That one goes there. And then 2, comma 1 goes 3, 2. So it's 2 there and 1 there. That's right. And then 1, 2 is 3 minus 1 is 2, comma 2, right? Because y is 2, and this then is also 2, which is exactly right. We have 2, 2. And then if we go out one more, we have 4 minus 1 is 3 for this, and then 1 is 1, and so on. So it works. So this maps this into this. Then we construct a bijection from A into the positive integers. So let's see if that works. So 1, so we want to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So 1 is, this is 0, and then 1. So 1, 1 equals 1. And then 2, 1 is 1 times 2 is 2. Half of that is 1. Plus 1 is 2. That's right. So this is 1. That's 2. And then is this one 3? We have 2 again, so it's 1 times 2 is 2. This is 1. Plus 2 is 3. 4 is 3. We're back down to 3, 1, and we want that to be 4. So 3 minus 1 is 2, times 3 is 6. So this is 3 plus 1 is 4, and so on. Good. So it works. So we started with z plus cross c plus, and then we were able to map A onto the positive integers. So this isn't really a proof. I'm just checking that it works. If you want us to prove it, we can. Let me know in the comments. So this picture might look familiar to you, and we're hinting here at the proof of one of the most famous and bizarre things that we learn at some point in our studies, which is that rational numbers are countable, that we can map the set of all rational numbers onto the set of positive integers. That is, insanely, there are the same number of rational numbers as there are positive integers. Or to be more precise, there are not more rational numbers than there are positive integers. Neither one can be determined, and both are countable. So we're going to prove this explicitly in the next video, but if you haven't seen this before, see if you can figure out how. How do we take what we just did here, and how do we use this to prove that rational numbers are countable? Okay, we're going to look at one last definition briefly to show where we're going next time. As I pointed out earlier, the fact that some infinite sets are countable must mean that there are other sets that are not countable. What can that mean? We'll start looking at that next time. Okay, next definition. A set is said to be countable if it is either finite or countably infinite. A set that is not countable is said to be uncountable. So this is sort of obvious, but there's just one little detail here that we actually consider finite sets to be countable also. Okay, and then if it's not countable, it's uncountable. So I just want to point this out again. There's an interesting parallel between the difference between finite and countably infinite and countably infinite and uncountable. So finite means that there is a bijection from B to a section of natural numbers. And then infinite means that there is not such a bijection. Countably infinite means that there is a bijection from B into the set of positive integers. And uncountable means that there is not such a bijection. Okay, so next time we're going to prove a theorem about countable sets that parallels the three-part theorem we proved last time. Please come back because the proof is really interesting. It starts out very simply, and then suddenly out of left field we hit a huge roadblock that forces us to rethink or maybe modify the logical underpinnings of our proofs. See you next time. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.